All right, so all right, so I graded your last lab, and I sent you media comments about it. If I had a lot of feedback to give you, I sent you a voice recording basically, which hopefully works for people because it's unpleasant typing really long paragraphs in Canvas. Um, it's a lot quicker for me to use a voice recording. So hopefully that works. If there's any issues with that, let me know, and I can go back to typing comments. But anyway, so I left you some feedback. Lab 3, right? So most people in the end came up with a good circuit diagram for the traffic control system. Most people lost a lot of points because they didn't follow the steps of the lab, though, right? Creating an unsimplified product of sums from the truth table, and then sketching a circuit from that, and doing the same for sum of products and so on. Um, so with that in mind, I've posted a list of clarifications and a grading guide for Lab 4, okay, to explain exactly how I'm planning to assess your Lab 4. So this is posted on Canvas, okay, it's in the assignment. Let me just run through this, okay, we've already talked about some of it. And some of it we still have to get to. This last business of half adder, full adder, we're going to talk about in a few moments. But let me bring up the lab for comparison. Okay, so this is lab 4. It's 2 experiments. Okay, first experiment is working with the 7-segment display. You're going to implement a circuit in part A and match the switches on the left. Match the switches with the segments that light up in response. So you build a circuit, you flip these switches, different segments will turn on and off. Okay. Experiment 2, you're going to build this circuit and simulate the circuit, right? Put it in Tinkercad, generate a table that matches all binary equivalents of switch values with observed numbers on the 7-segment display. So you're going to flip around different patterns of these 4 inputs. You should see different things being displayed. Okay, so let's look at grading for experiment 1. Basically 10 points total. Experiment 1, implement the given circuit, make a table showing which switches correspond to which display segments. This should be a table with a left side and a right side. The left side should say, left switch 1. The right side should say, B, that lit up segment B. Left side says left switch 2. Right side says D, it lit up segment D, right? So you're going to have 8 rows, 1 for each of the switches. 4 left, 4 right, right? Corresponding to, those 4 switches and those 4 switches. And next to each one of those, tell me which of the segments light up, labeling those segments using this picture. Okay, so A, B, C, D, E, F, G, and if one of them lights the decimal point, DP. Okay, and then for experiment 2, part B of experiment 1, right, same thing. You're going to have a table, 16 input combinations, so 16 rows, and next to each input combination, draw me a picture of what you see on the display. Okay, so if you see something that looks like, the number 6, draw a picture like that. If you see something that looks like the number 5, draw a picture like that. If you see something that looks really weird like this, draw that, right? So I want to see what you observed as you went through all 16 input combinations in this display. And, the first 3 times I highlighted in here, when you make those tables, include them in your report, okay? That should be pretty clear, but I still have students who, it says, make a truth table from your circuit, and in their lab report they'll say, and then we made a truth table, but there's no truth table to look at, right? So everything that you do, put it in your report, okay? Alright, so experiment 2, this is where most of your points are going to come from. You're designing and implementing a 2-bit adder. Okay, 2-bit adder takes 2 2-bit numbers and produces a 3-bit sum. Now, in the end, the final circuit you come up with is going to drive this 7-segment display, so you're going to actually see numbers like this, okay? But most of this experiment, I want you to be thinking about building a circuit that takes in 4 bits, that's 2 2-bit numbers, and produces 3 bits. Okay, so 4 in, 3 out. So the simplified version of what you're supposed to do, make a system diagram, okay, make a truth table, write the minimized output functions, either sum of product or product of sum using K-map, and then step 4 says either using these previous results or research into possible designs, draw a schematic to implement the 2-bit adder with carry. Okay, at that point, when you actually make the schematic, which is a wiring diagram, that's where you're going to introduce this CD4511 to drive the 7-segment display. But everything before that, I want you just thinking about making a 2-bit adder. Takes in 4 bits, produces 3 bits. Let's see, question for Lab 4 Experiment 1, Circuit A. The circuit doesn't do anything when I flip the switches. Okay, so that's probably an issue with how it's wired. Make sure that the 7-segment display, you said common should be cathode, not anode, and double check the wiring. And if you're still not getting anything, catch me in office hours. We can screen share your Tinkercad session and see what's going on. All right, so let me show you the grading guidelines for experiment 2. Tell me what you're trying to do in this experiment. Okay, don't just start writing truth tables and equations. One sentence will suffice, right? In experiment 2, we are building a 2-bit adder to drive a 7-segment display. Something like that, okay? 5 points there. Show me a system diagram for the system you're building. I want that diagram to have 4 inputs called A1, A0, B1, and B0. Okay, A1 and A0 are the most and least significant bits of your first number, B1, B0, most and least significant of your second. And then 3 outputs called S2, S1, S0. 2 is the most significant, 0 the least. We already did this last Thursday. We made a truth table for this, this particular setup. Okay, so your system diagram has 4 inputs labeled as such, 3 outputs labeled as such. And just explain what they do, right? B1, B0 are the most and least significant bits of your second number B, A1, A0, or A. S is the sum of A and B. S2, S1, S0 are the 3 bits of that sum, okay? When you write this description in this picture of the system diagram, ask yourself, somebody else looking at what I've written, could they possibly interpret the circuit differently, right? If you just say the sum is S, well, what is S2? Is it the most significant bit? Is it the least significant bit? Is it the bit in the middle, right? The sum of what? The sum of all 4 bits coming in, or the sum of 2 2-bit numbers, right? So really think about this, because this helps you pin down what it is you're trying to do, okay? So give that some careful thought. Okay, and then write a truth table to correspond to whatever behavior it is that you're after. So your truth table will have 4 inputs, 16 rows, 3 output values, and the inputs and outputs should be labeled the same as they were in the system diagram. 2 inputs, A1, A0, B1, B0, 3 outputs, S2, S1, S0. Okay, so now you're up to a bunch of points. Okay, next, using that truth table and K-maps, and show me your works on the K-maps, come up with 3 simplified equations. S0 equals, S1 equals, S2 equals. Each of those is either a product of sum or a sum of products. Okay, so 3 simplified equations. That's worth 15 points, 5 points each. Okay, and then this is where you mention that you're going to take that 3-bit output and you're going to use that with the CD4511 to drive a 7-segment display. Okay, that's going to be done using what you learned in experiment 1. All right, now for the branch point. Okay, up to here you've got 3 equations for your 3 output bits in terms of your 4 inputs. You have a choice. You can take those 3 equations you came up with and you can build a circuit based on those. Okay, these equations are going to be pretty complex. So that's not the recommended way. The recommended way is going to be to basically forget about all of this and do something totally different. And that is to use what we call a half adder, full adder design, which we're going to talk about after this. Okay? If you decide to do the half adder, full adder, you still need to have all of this stuff up here to get your however many 5, 10, 20, 35 points from these earlier steps. Okay? But then at that point, right, instead of using these equations to wire up your circuit, you're going to go back to the drawing board. Okay, you're going to describe what a half adder full adder circuit does, how they're going to be connected to each other, right, which we're going to go over. You're going to write the truth table for a half adder, and then write out a simplified equation for the two outputs, right, using K-maps, showing your work, all that usual stuff. And then you're going to write a truth table for a full adder, which is a 3-input, 2-output device. Use K-maps, write simplified equations for those outputs, and then turn those two circuits, those two sets of equations, and this block diagram into a wiring diagram. Okay, so if you follow these 4 steps, you will end up with a wiring diagram for a 2-bit adder. If you take your 3 equations from the sum of products or product of sums up here and turn that into a wiring diagram, you'll have a wiring diagram for a 2-bit adder. Okay, but you'll have 2 fundamentally different circuits. Okay, please, please, please do all of these steps. Even if you decide you're going to go with option B, which is the recommended one, make sure you do all of these first. Okay, I cannot stress that enough, and no matter how hard I stress it, about a quarter to a half of the students, when they turn in this lab report, they don't do any of this. They start off with a half adder, full adder design, and they end up losing, a majority of points. Okay, so do all of these things, and then decide if you're going to go with option A or B. And if you're doing option B, then go ahead and do these things. Okay, whichever way you go, now you've got a wiring diagram, and I want that to be a wiring diagram that includes pictures of the switches, properly connected, all of the LEDs, the resistors, the power connections for the switches and the LEDs, part numbers, right, U1, U2, U3 on any chip, inverters, AND gates, and so on, pin numbers where you connect to any of those chips, and all the wires, and a component ID block. Okay, and you got to have all of those. Okay, but for the 7-segment display and for the CD4511, those are not standard components. They're not like a simple AND gate or an inverter. So for those, I want you to just draw a box, right? Label it, U1 or U2, whatever this device is called in your component ID block, and you can just label the inputs and outputs with the names that they have from the data sheet. So the 7-segment display, the inputs to that are labeled, A, B, C, D, E, F, G, and common, right? So you can use those in your box. You don't have to draw a picture of the chip. You don't have to cross your wires over to the actual pins, right? Just label them with the labels that you find on the data sheet. Okay. Once you have your wiring diagram, implement it in Tinkercad. Okay, and you should be able to use your wiring diagram to help you implement it. Okay, put pin numbers on everything so that you know which wires go where, and use the wiring diagram as a guide for building the circuit in Tinkercad. Build your circuit, test it, and then show me that it works by taking pictures of your simulation for at least 5 different input combinations. For example, 1 plus 2, 2 plus 2, 3 plus 3. And for each of those, right, you'll have your big long circuit here. You'll have your 2 sets of 2 bits. So if you want to do 2 plus 2, set the switches to say 2 and 2, and your display should show a 4, right? So do a screen capture on Tinkercad for at least 5 input combinations and put those in your report. And when you're writing your report, okay, remember, all of your reports have to be typed. Okay, you cannot handwrite your report. The only parts that can be hand-drawn are figures, so system diagram, wiring diagrams, things like that can be neatly hand-drawn. But, make them clean pictures, crop them to the right size, paste them into your report where they belong in the report. Don't just put them all at the end. Okay, when you take these pictures of your Tinkercad circuit and you put them in your report, put a label on them, right? For example, if you showed me that 2 plus 2 equals 4, put a label right under that figure saying, circuit showing 2 plus 2 equals 4. Just one sentence is all you need, okay? But you're trying to make this a document, okay, that explains what you did and covers all the details of it. So don't ask the reader to try to guess what this set of 6 figures and 2 K-maps is at the end of your report, right? Label stuff, okay? And then as usual, cover page, conclusions, lessons learned, new experiment, all of that stuff. Okay, any questions about that other than the details of half adder, full adder, which we're going over next? But as far as what I would like to see, how I would like to see it presented, any questions about those details?
Is it all right if we handwrite equations?
Yeah, so if you do it neatly, and if you put them in the text wherever they belong, yes, you can handwrite equations, because it's easier to put bars on top and things like that by hand than by typesetting.
Okay, cool.
Mm-hmm. All right. How do you make a table showing which switches correspond with which display segments? So this is a question I'm guessing for experiment 1. So which switches correspond to which display segments? So your circuit looks something like this. You have a left bank of switches and a right bank of switches, and you have a 7-segment display. So I would just do something like this. Let's not do that. So
just pretty much 2 truth tables for the left and right.
yeah. So you can do something like this: left 1, left 2. Right, and then your segments are labeled A, B, C, D, E, F, G, and D, P. So maybe this is A, and this is D, and this is F, and this is G, and so on. All right, anything else?
So if it's handwritten, as long as it's neat, we can put it into the lab report, right?
Say that again?
So if we handwrite like truth tables, the K-maps, as long as it's neat, we can add it into the lab report.
Yeah, I mean, you definitely want those things in the lab report, and yeah, they can be handwritten as long as they're neat. And like I say, generally when you put things into a report like this, it's good to make sure that they're cropped to a reasonable size, right? If I were to, I would want something neater than this. But if this was to be my table that I was doing, I wouldn't want to just take a picture of this, with my pencil there and stuff like that. I would want to take it and crop it, right? So it's just that, and then paste it into the report, and put a label under there. Switch to segment comparison experiment 1A, something like that, just to make it clear what it goes with. And if you're not sure how to crop and edit pictures, right, let's talk about that office hours or something for anybody. Like I say, I used to live in Windows. I used a tool called IrfanView. IrfanView. It's free. It's very lightweight. It's super reliable, and it's really easy to do things like crop and image. If you're in Linux, there's tons of tools available for this. Most of them pretty lightweight. There's something called the clipping tool in Windows that some people use. OS X, I assume, has similar tools. So, develop a tool set. It will work well for you for whatever you're doing throughout school and, beyond. You're always going to be making reports. And so this can be a good excuse to, further develop your tools for manipulating images and rotating and adjusting background intensity and all that sort of stuff. And once you have a good tool set, it's actually pretty fun to do those things. All right, so let's talk about half adder, full adder. Because if you build a 2-bit adder the way we've been describing it, right, it's got 4 inputs and 3 outputs. And so there's 16 rows and 3 columns. So that's 48 output bits. And, you know, a good chunk of those are going to be ones. And, you know, if half of those are ones, 24, that's a literal count of, you know, some huge number. It's 24 product terms you're going to have to create, 24 AND gates you're going to use, and then OR together in some combination. But suppose you wanted to make a 4-bit adder. So suppose you wanted to add A0 through A3 and B0 through B3 and produce a 5-bit sum. Well, you have 8 bits coming into this. That's going to be 256 rows worth of truth table. And you're going to have 5 output columns. So you're going to have, you know, 1,200 plus ones and zeros in here, right? Each of these is going to have nominally 128 one terms, which means at least unsimplified 128 AND gates. And then a big OR gate that ORs 128 things together. Now you can do some simplification, but try to make a 32-bit adder like this. 32 bits for one number, 32 bits for another number. That's 64 input bits. That's 2 to the 64th rows in your truth table. That's crazy. Okay? 2 to the 64th is like, it's like a big number. I was going to say a billion, I think. So there's a better way to design an adding circuit. Okay, and that is to think about addition the way we do addition by pencil and paper. So when we want to add numbers together, we go column by column, right? 9 and 6 is 15. Well, we write down the 5 and we carry the 1. 1 and 5 and 3 is 9 with no carry. 4 and 2 is 6. And we're not using a big wide truth table in our brains, right? We're really doing this one column at a time and just sort of carrying this extra digit over if we got a sum that was bigger than 9. Okay? If we try to do this in binary, we do exactly the same thing. We do 1 plus 1 is 2, right? So we put a 0 and we carry the 1. 1 plus 0 is 1 with a carry of 0. 0 plus 1 is, again, 2, so that's 0 with a carry of 1. 1 plus 0 plus 1 is 2, so that's 0 with a carry of 1. Let me make this a 0. 1 plus 0 is 1, and a carry of 0, and 0 plus 1 is 1. And I did not use, you know, a 12 column truth table, even though there's, you know, 2 to the 12th different ways that I could have chosen to add 2 6-bit numbers, right? I just did this column by column. So if you think about the steps in doing this, what do you have to do? Basically, all you have to do is be able to add 3 bits together, right? An incoming carry bit, a bit from your first number A, and a bit from your second number B. If you can add those 2 bits together, the sum that you get, right, the least significant bit of the sum goes down here, and the most significant bit of the sum is a carry into the next stage. So 1 and 1 is 0 with a carry of 1. Now I add that carry plus 0, 0, I get a 1 with a carry of 0. I add that carry with a 1 and 1, I get a 0 with a carry of 1. I add that carry with a 0, 1, I again get a 0 with a carry of 1. I add that carry with a 0, 0, and I get a 1 with a carry of 0. I add that carry with a 1, 0, and I get a 1. So the idea is, let's define a block that does exactly what we're doing by hand. And this is something called a full adder. And a full adder looks like this. It has an incoming carry bit. It has an incoming bit A and an incoming bit B. It has an outgoing bit called sum, and another outgoing bit called carry out. And now you know why the arrows are important, because we don't always put the inputs on the left. Okay, what does this full adder do? It adds the carry in A and B, and it produces a 2-bit number. The low bit is the sum, the high bit is the carry out. So if we were to draw this as a truth table, we'd get something like this. And let's look at carry out. Well, let me put a separate column in here, which is B plus A plus Cn. What happens if we simply add these 3 bits together? What value should we get? Well, if they're all zeros, we should get a 0. If they're 0, 0, 1, we should get a 1. 0, 1, 1 should give us a 2. 1, 0, 0 gives us a 1. 1, 0, 1 is 2. 1, 1, 0 is 2. And 1 plus 1 plus 1 is 3. Okay. I'm going to write down my actual output as the carry out bit and the sum bit. And this is just the binary equivalent of what we want this B plus A plus C in to be. So 0, 0, that's 0 with no carry. 1 is 1 with no carry. 2 is, the number this. That's a sum of 0 with an outgoing carry of 1. 2 is a 1, 0, 2 is a 1, 0, and if our sum happens to be 3, then our sum bit that we would write down, right here, is a 1, but we also have this outgoing carry that we carry into the next stage. So this truth table describes what this full adder does, okay? But let's forget about the truth table for a moment. Let's just think of this logically in terms of, I want to do this kind of addition. And you can put these full adders together in a really clever way. So here's a full adder. And here's another full adder. And what I've done is I've taken the output of one full adder and fed it to the input of another full adder. Alright, let's see question. What if there were 4 inputs instead of 3? Would it still work the same? A full adder is by definition only taking in 3 bits. So it's not a full adder anymore if it's 4 bits, but we can actually do 4-bit addition by using a series of full adders. Alright, so here for example, I have an original carry in, I have 2 bits A and B coming in, I'm producing a sum, but the carry that's coming out of here is going into the carry in of this next adder. Okay, that's carrying, 1 plus 1 was actually 1, 0, so I got a sum bit of 0, and that 1 got carried over to the next column as a carry in being added to those next 2 bits. Well, that carrying from the output bit here to the next stage's carry in, that's what this wire does. All right, that's just a plain old wire. So yeah, each full adder corresponds with 1 digit in the sum, or 1 bit digit in the input is a little more precise. So this could actually be A0, B0. This could be A1, B1. And so what's my first sum bit, which I'll call sum 0? Well, it's A plus B plus my Cn. I'm just going to connect to ground because, you know, the first least significant bits that we add, we don't have a carry coming in, right? So it's just going to be the sum of these two bits. So my first carry in is 0. This is my sum bit, but the carry out goes into the carry in of the next stage, where I add bits A1 and B1 to that incoming carry, and that gives me my next sum bit right here. And if there's a carry out produced from here, that's going to actually be my final sum bit. Okay, so this is a simpler circuit, right? It's got 3 inputs, 8 rows. I can make the truth table by just seeing what the sum of these are and writing them in binary. The carry out is a really simple function. If you make a k-map for this, right, carry out is going to have 2 expressions, 2 product terms that you have to sum. The sum is actually going to look a little awkward in a k-map. You're going to get a checkerboard. But remember, I said checkerboards, think about exclusive ORs. So this would be a sum of 4 product terms, or you can do it with a pair of XORs. Okay, so you play around with that. You look at the k-maps, you write simplified equations, you come up with a pair of really simple equations for carry out equals and sum equals. And you'll find that building this circuit is pretty simple, way simpler than writing the circuit for just, you know, the straight truth table of 4 bits in, 3 bits out. Once you know how to build a full adder, you make yourself 2 of them. You connect the output here to the input there. You feed your first pair of input bits to those inputs, next pair to there. Set that initial carry in to be 0, and your 3 bits coming out, your 2 sum bits, and your final carry, that's your sum. Okay, this takes some experimenting with. What I'd like you to do is, when you get home, play around with this, okay? Mess around with this, make your own version of the truth table. Don't just take it from what I've said here, but try to come up with the truth table, because that'll help you, you know, further understand exactly what this is supposed to do. And then think about if you had this circuit and you put 2 bits in here, 2 bits in here, what would this do, right? Convince yourself that this actually produces a 3-bit sum of that 2-bit number and that 2-bit number. Okay. Now, for the sake of discussion, let me just show you what you can do. Bang, there's a 3-bit adder. I could put in a 3-bit number, A0, A1, A2, another 3-bit number, B0, B1, B2, and I will get out a 4-bit sum here, 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 and here. And you can chain these things together as far as you like. You can make a 32-bit adder by taking 32 of these things, just hooking them up side by side. Feed in your inputs to the top, and your sum will pop out the bottom. Okay, this is modular design. This lets us make more and more complex circuits without increasing the difficulty for us. Okay, it's not the most efficient design in the world, but to make something that will add 2 32-bit numbers, it's very straightforward. And if you're working in a system like, you know, in Tinkercad, for example, if you can cut and paste circuits, once you make one of these, you may be able to just plop down copies of it, connect the outputs to the inputs, and you've got a nice big circuit. Okay, so that's one comment. But let's stick with the 2-bit case, because that's all we're worried about for this lab. So the carry out is some bit 2. And this is a full adder. So what is the half adder for? That's my next sentence. This first full adder, you notice the carry in is always 0, right? When we add numbers in binary, we never have a 1 that we're going to add to this least significant pair of digits. This is always a 0. We're really just adding 2 bits. Well, a full adder is capable of adding 3 bits together, but this one particular full adder only has to add 2 bits. The incoming carry is always 0. So we use a different circuit called a half adder. And a half adder is really just a truncated full adder. It takes in 2 bits, A and B, produces a sum and a carry out. Which means it's really just the full adder where we only pay attention to the rows where the carry in is 0. So it's a simpler system diagram, only 2 inputs. The truth table is only going to have 4 rows, and there's no carry in. Okay, so that's a half adder. And it's even easier to build than the full adder. And so we can replace this first full adder that we set the carry in to a 0 with just a half adder. And so there's the other way to build a 2-bit adder. And this is a whole lot less circuitry than just working from the straight truth table with 4 bits in, 3 bits out. Now it takes a lot of analysis to get here, right? Which is the whole point of the lab, is to go through that analysis and to document it. But once you get to this point, right, now you take the truth table for a half adder, you simplify the equations for the outputs using K-maps. You make the truth table for a full adder, you simplify those equations using K-maps, and you make wiring diagrams for these. You feed your inputs to those spots, you take the carry out from here, feed it to the carry in there, and your sum comes from those 3 spots. It's going to be a lot simpler diagram, which means a lot easier to actually implement. Okay, so that's the famous half adder, full adder approach. All right, other questions about that? And when I ask if there's any questions, I don't mean that to say you should understand this perfectly now, okay? I'd like you to understand it well enough to have an idea what this is that we're talking about, a good enough idea that you can go off and you can work with it more, you can actually sketch out some of the equations and see how this thing works.
For the full outer truth table, how'd you come up with the sum?
So I looked at what I want A plus B plus C in to be. So for example, if I want those 3 bits to add up to 2, what is 2 in binary? It's 1, 0. Okay, so the sum is the least significant bit, the carry out is the most significant bit.
Oh, okay.
Right, so 0, 0, 0, 1, 0, 1, 1, 0. Right? The sum of those 3 bits, that's just exactly what the carry out and the sum out are. Just to be clear, you're adding 2 2-bit binary numbers and receiving 1 3-bit binary number, right? Yes, in the end, that's what your final circuit is doing. So if you build this, you're receiving 2 2-bit numbers, right? A1, A0 plus B1, B0. And you're getting out sum 2, sum 1, sum 0, or what I've been calling S2, S1, S0. So 2 bits plus 2 bits equals 3 bits. That's correct. Does this only work, I'm guessing, does this only work for the 3 inputs you have? Yeah. Does what only work for the 3 inputs you have? So a full adder is a 3-input device, right? So a full adder is specifically a 3-input, 2-output device, right? But we could use it, for example, to add, numbers A and B, where those had 4 bits each, right? We could string 4 of these things along. We could feed the 4 bits of A into the 1, 2, 3, 4 adders, and the 4 bits of B into those 4 adders. And we would get 4 sums and a carry out. That's a 5-bit final answer. But the full adder always looks like this, right? 2 bits and an incoming carry, and then an outgoing carry and a sum. Would it ever switch from a 3 to 2 device? No, not for a full adder. So there's different versions of this for matters of efficiency and such, where we might have other devices that had extra inputs or extra outputs, but a full adder is always 3 in, 2 out. And we just put those together, and you can put them together as many as you want to add, larger numbers of whatever size you need. But that's the building block for a full adder, and for a half adder, it's 2 in and 2 out. And you can fake a half adder by just taking a full adder and tying that extra input to ground, right? But the idea is, if you just design a half adder, it takes a lot less circuitry. Okay, these are good questions. Definitely keep them coming. All right, anything else on this? So you've got until Friday to do this lab. My hope is that everybody has done the earlier parts of this lab that we had already talked about, right? Basically down through this part where they were just working from the truth table, right? Stuff we went through Thursday, and I said we'd go through this today. So I'm hoping that people have already done, these earlier pieces, and that now you're ready to, work on half adder, full adder design, write that up, and go on from there. Is there an instrument on Tinkercad that represents a full half adder? There may be, but if there is, you're not allowed to use it. Okay? We want you to actually do, the whole circuit design and implement it yourself from primitive gates, ANDs, ORs, NANDs, NORs, XORs, XNORs, and NOTs. But in practice, right, if you go to a chip supply, you can get chips that do half adding and full adding, usually multiple bits. But yeah, if you find it in Tinkercad, don't use it. Build it up by hand from these first principles. All right, so the lab you have until Friday. The homework I extended until next Wednesday because we've started going through some of what we're going to do. But 2 things. One, the material for the homework, the material in this chapter, is extremely dense. Okay? We're going to learn new concepts. We're going to learn techniques and algorithms for coming up with the answers to these analysis questions. But they're very complex. Okay? These later homework questions can easily take you an hour apiece once you know what you're doing. Okay? Longer than that to figure it out. And I don't want you to be time constrained by, a Friday deadline. So the next homework is not due until a week from tomorrow, okay? Your midterm is a week from today, and we'll cover some of the stuff that we're going over now and the stuff on this current lab, okay? So don't just push this off until, next Wednesday morning or something. It will take a long time to do the homework. Okay, but it's the only way that I know of to actually learn the concepts for what we're going to call state machine analysis, okay, which is the point of this chapter, or the punchline of this chapter. The only way to do that is to actually work through the analysis process yourself, and it takes a long time. Study guide for the midterm. Everything we've done so far, I guess. I can put together a list of topics maybe, but it's really just going to be, go over your labs, go over your homeworks, and all the stuff in the chapter that was used in the homeworks. That's pretty much your best study guide. Um, Representations of numbers, two's complement, addition, subtraction, sum of products, product of sums, K-map simplification, covering ones, covering zeros, min terms, max terms, compact form, all of that stuff. And the lab stuff. So half adder, full adder stuff will probably be on there in some form. So make sure you go over that. Programmable logic, PLAs, PALs, and PROMs, that's fair game. Really just go through the homework, look at the homework questions, and I'll pretty much pick problems similar to what you've done there. And circuit design, right? You'll probably see a problem where I say, build a voting machine that does such and such. Here's a description of it, and I'll ask you to give me a system diagram, a truth table, simplified equations, and then sketch a circuit diagram. Logistics for the midterm may be interesting. So it appears everybody has an ability to take pictures. I'm hoping most of the midterm can be done by typing, but there's going to be parts of it that you're going to have to draw by hand and then take pictures and submit those. If that's likely to be a problem for anybody, let me know right away, okay, because I need to take that into account. But it's a whole lot easier to do the testing and to take the test, right, if you can draw a picture of a circuit diagram instead of trying to, cobble it together with a piece of software. So if you don't have the ability to take a picture and upload it to Canvas pretty efficiently, let me know. Send me an email like today, so that we can figure out what to do about that. Yeah, it'll be a 1 hour exam.
So, are we gonna hold a lecture on our exam day?
Yeah, I'll plan on lecturing afterwards. I don't know how many questions. I haven't written it yet. Um, a handful of questions. I don't know. I haven't put it together yet. And like I say, it's a different modality. I've only done a few online exams like this. So trying to figure out, how to ask a good collection of questions but not overwhelm people, because it is, a different way of taking a test. It may be a bit experimental, but the grading will, hopefully take that into account. Meaning if I do something ridiculous and I give you an impossible exam that takes 5 hours and nobody gets anything done on it, right? You're not all gonna fail. That's my failure there. So, or if I give an exam that's so easy to do, everybody gets 100 and they're done in 10 minutes, right? Well, you'll get to keep your 100, but the next time I do this, it'll be a harder exam. So it's a process, right? But I'll try to make it a fair and reasonable exam. All right, good for now. Let's go ahead and take a 5-minute break, and then we will come back and we'll start digging into the chapter, looking at memory circuits, building our way towards state machines. All right, and this is where stuff gets really good. All right, so I'll be back in about 5 minutes.